Well, then I'll just go ahead and get started. I'm Roger Jepson. I'm a software architect with Intel's Data Center Storage Group. So I'm out of Chandler, Arizona. And Nate and I swapped because I'm going to talk about some of the storage features that are in IA processors, and the things that he's going to talk about take advantage of those features. So obviously that's not the thing to make it go. There we go. So we'll start out by once again just kind of doing that 100,000 foot view here of Intel storage technologies, an orchestrated data center where you've got your deployment and management layers and architecture kind of layer up here. Then you've got your middleware software layers down here, and then your hardware pieces. I'm going to focus mainly on the core processor, some of the things that we have particular features and instruction sets that the libraries take advantage of. This over here is the data plane development kit and the storage performance development kit, a set of storage libraries that are able to, I'll just say this, accelerate storage technology. Nate is going to cover more in detail of that. Then I will focus on within the processor what we've done to be able to increase I/O bandwidth and what we're doing generation over generation. And then I'll end with an item we call our QuickAssist technologies. Okay, so let's start then with processor enhancement. So, generation over generation, we take advantage of Moore's law, obviously. So when we're able to get, put more transistors into a package, lower the power and things like that, we're going to always try to increase the number of execution buffers, execution units, so we can get more parallel instructions and threads going. Also, one of the things that we've added for storage in particular is there are specialized CRC instructions for data protection. And then, I'll talk about that when we get to the IIO unit. Also, there's the advanced vector extensions, AVX. Starting with our Ivy Bridge generation, it was 128-bit vector operations that you could do simultaneously. Haswell, Broadwell brought it to 256. Our new Skylake processor brings it to a full cache line 512-bit vector operations. And this is one of those areas that our storage libraries take advantage of, particularly like for doing core-based RAID, XOR, RAID 5, P plus Q, RAID 6. And I'll tell you, our performance here is that you can do these RAID operations using the storage libraries in less than sub-cycles per byte from the CPU. So it's very, very fast, very scalable across cores. Also then our secure hash algorithms, you're able to do your SHA type algorithms for hashing to be able to fingerprint data for your dedupes, deduplication operations and things, indexing for being able to hash and put into file system locations. And then also we've got some new instruction sets that for AES encryption. And then also Intel transactional synchronization extensions for lock collision. Now, are you guys familiar with that TSX technology?
Nope. No.
Okay, so
I was looking at that wondering what Larry Ellison had to do with transactional synchronous extensions.
Oh, okay. Okay. Oh, Larry Ellison, I see for this. Lock collision. Okay, gotcha. Got it. Because I was thinking, like, where did he get that? Okay, so
just to point out, Elysian is a word you can't expect people to know.
Okay, so very briefly then, what this TSX technology does is that it allows now to where what we've done is we've done detection circuitry into the hardware, into the processors. This debuted with Haswell server CPU, so the what we would call the HSX. Okay, so it's not in the client CPU, but it debuted in with the server processor. And what it does then is that today, when I run a multi-threaded application, all of them come along, and whenever they hit an area that's critical code where they're sharing data, they each go call into some kind of a lock API, and they're trying to acquire a lock. Every time they have to go acquire the lock, they either get it But they have to take that initial hit to make the call to try to get that lock, or they're waiting for that lock to be available. So what TSX does now is that we've got some shadow area that we run on a per thread basis. So now you can have multiple threads running, and then what happens is that when these threads come along to where they're hitting critical code sections, so you still in your application would have your critical code sections marked where they would attempt to get a lock. But what happens now is the hardware automatically speculates that you got the lock. And then what the hardware does on a per cache line basis is that it monitors to say, okay, when these threads are running, do I ever get more than one thread trying to access the same cache line? And if it doesn't, then what happens is that the speculation goes through, that shadow context is committed, and that shadow context is part of the all the coherency engine, and it's all globally visible, and that thread completes and executes. Okay? Whereas if the hardware did detect that another thread was colliding on that particular cache line, then all that happens is that the shadow context is discarded. Then it takes the processor takes the execution or the instruction pointers of these threads, moves them back to the beginning of their critical code section, and they go through and run the way they do today, where they try to acquire a lock and get things done. Now, what we found in our testing is that when you're at runtime and threads are going, there is not that much collision as you would think. And so what we try to do then is we try to say, look, then we'll run speculatively, allow the threads to assume that they got the lock until hardware detects a collision on a cache line. And then we'll roll back if we need to. And so multi-threaded applications can get roughly about a 30 or more % improvement in their application performance. So that's what TSX is. Okay. The other thing is here, and now I know we're talking mainly about storage, but I wanted to bring up virtualization here, some of the things that we've done for virtualization. And the reason being is that server-based storage is becoming now kind of that building block for what next generation type storage appliances are kind of headed towards, and particularly with hyperconvergence, which heavily relies on virtualization. And so some of the things that we've done here with our VTX, VTD technologies, VTX is where we're actually doing CPU virtualization. Okay? And then the VTD with the directed I/O, that's where we're doing I/O virtualization. And some of the things that we've done there is that, like for example, a VM control structure, every time that a user VM is going out and trying to make something that normally that guest OS believes that he owns the box, it's going out and hitting this VM control structure. And every time that was a VM entry and then an exit. So you had that round trip latency and things like that. Well, now we do VMCS, or that virtual machine control structure shadowing. And what that means is that we're able to make it now to where you never that guest VM never really exits into the virtual machine manager to be able to make those calls and to be able to make those transitions. Also, the other thing that guest OSs would do, they think they own the APICs, and so there would be constantly these checks to be able to go look and see what the current privilege status is and things like that. We're doing APIC virtualization. Also, posted interrupts. So it makes it now to where you're able to assign an interrupt directly into that guest VM without having to go through and have it emulated through the virtual machine manager. And so those are some of the things that we're doing. Also with the VTD directed I/O, I can do a direct remap of, say, a virtual function device. So, I might have a network card that has a physical function and X number of virtual functions. I can assign that directly into a user VM, and then using this VTD, not only can I map all of his DMAs into that, but I can also redirect his interrupts. And so he looks like he's fully controlled, and I start to reduce latency now when I run an I/O device in a virtual machine. And then the other thing that we've added here is that within that VTD, because what VTD really does is it's an IOMMU, okay, to where there's a set of pages in there, privilege pages, to where when an IO is being directed or a DMA is being directed, it goes in based on that device's bus device function, looks up into a table. Hey, for the addresses that you're trying to hit, do you have the permissions? And if not, it's a page fault or it's a fault. If so, then the IO completes. And then one of the things that we've done here is that we've done 1 gig super pages of the IO translation look-aside buffers for that cache. So what happens now is that with the Intel virtualization technologies, I can take and run like a storage VM that's talking out and doing I/O. I can make it run to where it looks like the latencies are like that application was running on bare metal, not having taking the hits that by having a VMM there, a hypervisor there. Okay, and then in our IIO. Now, when I say IIO, normally we talk about cores and uncores. Okay, and the cores, obviously, these are the pieces then to where we have the logic that actually are running instructions. And then the uncore are all those things to where we have the fabric that interconnects all of the integrated memory controllers, the PCI root ports, and all those kinds of things. And so that's what I'm talking about when I'm talking about the IIO units. So what we've done here is generation over generation. We've increased the number of IIO buffers so we can get more traffic that comes through those. Also then, I heard you mention about the balancing between your throughputs, memory, devices, disks. So this is one of the other things that we've constantly been working on, and that is to make sure that we first off increase the number of PCI lanes so that we get that expansion, increase the number of credits, improve the arbitration so that we can get more packets going, and then to be able to get a good balance between the number of memory channels in a socket to the number of PCI Express lanes that are coming off of that socket, so that so that we don't introduce a new bottleneck. And so we've been working on that. And then one other thing that I'll talk about this in the next slide a little bit more detail, but we've added into our root ports then the PCI SIG defined multicast. And I'll talk about that. So first off, with these special features in our CPU, we call them our platform storage extensions, or PSE. And before I kind of introduce, there's only 20 minutes that they told me I have to talk to you about, so I've kind of just picked a few specific features to go and discuss. But before I do that, I kind of want to get you accustomed to a traditional storage box, enterprise storage box. Generally what happens is I'll have 2 active controller nodes, and they'll sit in the same chassis. And then what will happen is that they'll run dual active-active failover. So kind of like a cluster in a chassis, okay, in the same chassis. And so one of the things to facilitate that is that we've integrated a non-transparent bridge into our processors. And with Skylake, we're making it to where you can have up to 3 of these NTBs per socket. And what happens now is that through this is a means by which you can get high-speed PCIe or type speeds to where this is where a high availability link, your cluster traffic and that kind of stuff, your mirroring traffic, would be able to go low latency, high bandwidth over PCI Express. The other thing is that we have what we integrated in here is what we call our I/O accelerated technology DMA. We call it's codenamed. Oops, I went too fast. It's codenamed Crystal Beach DMA. We call it CBDMA, and you'll be able to find that out there too. If you were to go and look out onto the web and look for some specs, you would see this under CBDMA. But anyway, it's a series. It's a PCI Express root complex integrated endpoint. And it's got multiple channels of high speed or high performance DMA engine. And it has the ability to do, mem to mem copy to where within the same socket I can move data within a socket from one memory region to another, and I also can do it to memory mapped I/O. So for example, I would be able to say that, okay, if I have a large amount of data that I'm going to mirror between these two, I don't know why I keep doing that, but I'm going to mirror between these two nodes, I would be able to set up a descriptor in the CBDMA and then push that data across the, through the NTB. And one of the things that's nice here is that, you know, for example, if I was doing my transaction journal and I was in this dual active-active failover kind of system, boy, I keep, I'll just do this. And I'm doing this kind of, yeah. You know, if I was to do this, I might also, if I was doing RAID as my protection, I might have my RAID write-back cache, and I need to be able to mirror them between the two nodes so that in case of a failover, the other guy could pick up where the other one left off. The other thing that we have in our CBDMA is that we've integrated a capability called dual cast. So, and what the dual cast does is that when I set up a DMA descriptor for the CBDMA, I can say, well, okay, I need to be able to move data from one memory region to another, set in the descriptor that I want it to be dual casted to a different address, which might be the MMIO region of this NTB that then gets translated over to here. So what it means is I set up a single descriptor and I have just one memory touch. So it reduces a lot of latency. Instead of having to do multiple descriptors, multiple memory touches in order to do that, those memory copies and to make it also go remote.
So does the M2IO there imply that the processor in controller 1 can talk out the NIC in controller 2?
Well, only if it's memory mapped. And this is what I'm trying to say, because you know usually the way a NIC controller is, you got send receive buffers and things like that. And the beauty of this is that the way that the NTB is set up is that when you go into the PCI config space and you pull out, it has two sets of 64-bit bar regions. And so once those get mapped in, it's a memory window to where I can do direct writes through here, and then I can set up a translation register that says, well, once you write into that memory mapped I/O space, it'll get translated to an address that these two nodes have negotiated.
Right.
And so that's why. So it would need to be a memory device in order for it to work.
Okay.
Memory tech device.
So is the next version of Intel NICs going to be a memory device so I can do that?
Okay, no new product announcements here. Okay.
That was a really good try, though.
But you bring this up. So, and I should have mentioned this because part of what Nate's team, they do a lot of the software enabling, and I work with that team quite a bit as a software architect. But with the non-transparent bridge, not only do we provide a base driver that just at least makes this NTB available so that you can just do raw writes and things through it, but we also have a virtual layer, or I should say a stackable driver that goes on top of that. That then what happens is it makes that NTB look like a virtual NIC. Okay? And we do this for both Linux and FreeBSD. We have those drivers out there, and they're actually upstreamed already. And so then what happens is that it goes into and fits into a normal TCP/IP stack, and you get a very high-speed back-end media and link layer. But it fits into your normal TCP/IP, and that's what a lot of customers will use, is they'll be able to set that up and say, oh, okay, that's my high-speed cluster link, and nothing changes for me, it's TCP/IP.
Right, and so data goes via RDMA, and command goes over the virtual NIC channel.
So RDMA is not completely set up here yet, because we would need to be able to have that RDMA logic in place. You could do, like one of the things that we're working on right now is Linux has the concept of a soft RDMA, to where you can emulate that in software.
I was actually just thinking of M2M as using RDMA as very generic terminology, that it is. Essentially what it is. Yeah.
Yes. Yeah. But, I see what you're saying. That's the concept.
Right. M2M is remote direct memory access. It's just, it doesn't follow some APIs that you're thinking of that fall in. that narrow your definition.
Okay, so I'm getting the sign here that I'm going to need to wrap up. So I'll just say this. I've got this slide and one more, and we'll be done. But I had mentioned about the PCI Express root port multicast, and what it does is once again, it's designed to be able to reduce the number of memory touches and descriptors, and all the difference is that any traffic that's moving through the root port, I can set up a multicast set of tables. So when that address comes through, and if it gets a hit, because I've programmed to say when this memory range, when a target goes to this memory range, I want you to take and also direct it off to some other multiple memory ranges. And what we use it for is to be able to come in, target memory, also remotely go to the remote node. One other thing that we have is in order to do power failure protection on the system domain, we call it asynchronous DRAM refresh. It's completely a hardware mechanism. And basically what happens is that the power supplies, they have a certain amount of residual capacitive power. And they do an early fail system, a hardware trigger, that then we have some logic that captures that, sends it into the reset logic of the of our chipset, of our PCH chipset, which then informs the CPU, hey, you got X number of microseconds before we're going to die. And so then what happens then, flush I/O memory controllers out to, say, like an NVM DIMM, some kind of non-volatile DIMM. The DIMM gets put into a self-refresh, then allows to where there's a hit on a save pin to be able to save memory out. Now, in the case of the 3D XPoint, this save piece is not necessary, but yet that flushing through the IIO is necessary to make sure things get out to the DIMM. And it completes in under 100 microseconds, or in that realm. And the only drawback is it does not protect the CPU caches. But we do have a mechanism to where you could turn that signal from that early warning signal from the power supply. Instead of doing the ADR hardware flow, it could generate a system management interrupt. And then you have software control, and you could do like a copy to flash. And by then using standard bus master, you would be able to get all the CPU caches and stuff out there. And then here's our final piece here then, is our Intel QuickAssist technology. Now, what it is, it's high performance compression and encryption. I'm able to get line rate speeds with this. It's all hardware assisted. Today, it comes in two form factors: a PCH substitute, which is the chipset substitute, or in a discrete PCI Express add-in card. In the future, you're going to see it integrated into the CPU complex or into chipset, so it'll be more mainstream. But what it does then, high-speed, crypto using these particular algorithms. Also, it'll do your SHA hashes and your MD5, and then it will do compression, the LZS type compression, and deflate that you would see like with zlib. And
well, that's not good for XR.
beg your pardon?
I said that's not good for XR.
For XR.
Yeah, XR makes a card that you're going to put out of business with this.
Well, I tell you, it's being recorded here, so I have to be careful. But you know how the industry goes. So.